Hello everyone, my name is Ting from Department of Electrical Engineering, Cần University. Today I would like to make presentation about my topic is about optimal planning for sustainable hybrid energy systems, reducing oxygen on site, and considering byproduct hydrogen for backup power in our culture. The content of my presentation includes traditional shrimp farms, sustainable hybrid energy systems for shrimp farms, and the last one is case study and simulation results. Energy demand is one of the major challenges of the shrimp industry because most of the energy is consumed by water pumps and pond aerators, which run 24 hours per day to improve dissolved oxygen in ponds. Electric aerators constitute about 80% of farm energy demand, while pumping water accounts for 50%, leaving other uses at 5%. Farms are connected to the national grid and have diesel generator for backup. The big problem is that aerator runs continuously, resulting in off-gassing dissolved oxygen, wasted energy, high operation cost, and CO2 emissions. Therefore, I propose an optimal design on sustainable hybrid energy system for shrimp aquaculture industry. The constituents of the system are divided into resources, bioload, and shrimp ponds. The main bioload is electrolyzer. In the daytime, the primary power is generated from solar panels and wind turbines is converted to AC and impacted to the aeration system. The base load is supplied by stable power, while the remaining power is used to run the electrolyzer for producing oxygen in situ. Moreover, the byproduct hydrogen through water electrolysis is utilized for various applications, such as selling to the fertilizer factories or storing in the tank for generating backup power. The pure oxygen from the electrolyzer is compressed via a short-term oxygen tank to the micropump system at the bottom of ponds, which generates oxygen micropumps for shrimps. The innovative aeration system, which is aerated by pure oxygen micropumps with high oxygen absorption efficiency above 90%, instead of oxygen from the air 20%, requires less energy demand and releases less emission compared to the conventional aeration. The oxygen requirement during daytime in shrimp ponds is low due to oxygen supplement from photosynthesis, corresponding with low power demand from electrolyzer. Consequently, the electrolyzer is controlled to change its input power according to the amount of dissolved oxygen in culture ponds. When the system is well controlled, the energy demand is reduced, leading to low operation cost. In addition, the surplus electricity is sold to the national grid. At night, only wind turbine system might not produce enough energy for the power demand of the system, especially the electrolyzer due to the high amount of oxygen demand or at daylight hours when renewable resources cannot satisfy the power load demand due to the uncertainties of these resources. The deficiency in power is inevitable. In other words, when the imbalance occurs, The power backup system is employed to compensate for the mismatch of the system in islandless operation mode. And the robust optimal design of hybrid system for a shrimp farm is carried out at Vĩnh Châu, Sóc Trăng province. And the simulation results show that increasing the system cost leads to a significant decrease in CO2 emission. Nevertheless, the cost has negative values, indicating that the proposed system is able to obtain revenues from selling surplus electric power to the national grid and dump hydrogen to local fertilizer factory. The optimal solutions from Pareto front are divided into two groups. The group with organ solutions has cost values lower than the cost of the conventional aeration system, while the cost values of the group with bubble solutions are higher than that of the conventional aeration system. Solution 1 corresponds to the lowest value of the system cost and the highest amount of CO2 emission, while solution 2 is the intermediate solution among organ solutions. With the utilization of fuel cell as backup power in solution 2, the amount of CO2 emission declines considerably in comparison with solution 1 and the conventional aeration system. Under the cost of the system of solution 2 is considerably higher than solution 1. It is still significantly lower than the conventional aeration system. Hence, farmers could save about $28,000 per year. And that's all for my presentation. Thank you very much for your attention.